I want you to consider the mechanics of what happens when you look at a page of text. Whether it's an article on your tablet or a physical book open on your desk.
Right, you just glance at it.
Yeah, exactly. You glance at it, and without any conscious effort, you immediately parse the structure. Your brain just segments those blocks of text into paragraphs.
You see the white space and intuitively understand it's a break.
Right. You understand the hierarchy of headers, subheaders, body copy, and it all happens in like a fraction of a second.
Well, we process layout long before we process meaning. I mean, the human visual cortex is just a highly tuned pattern recognition engine.
Yeah.
It uses those spatial cues, margins, indentations, line spacing to build a mental map of the information before we even read the first word.
But to a computer, however, that spatial map it doesn't exist. A machine does not actually look at a page.
Not at all.
To a computer, text is nothing more than this linear, relentless sequence of characters. It's a single file stream of letters, numbers, punctuation marks, and invisible control codes.
Right, just rushing through memory. It has absolutely no intrinsic shape.
Exactly. And that's what we are getting into today. We are doing a deep dive into a really fascinating piece of source material to look at the friction between human visual formatting and machine linearity.
It's a great topic.
Specifically, we're looking at the exact moment a computer gets hopelessly lost because of a simple blank line.
Yeah, the broader challenge here is how we program a machine to infer context when all it has is that raw sequential data.
Which is surprisingly hard, right?
Oh, very.
Yeah.
It requires a surprising amount of counterintuitive logic to bridge that gap.
So our source material today is a developer journal entry published on May 22, 2026. The author is a programmer who goes by the name Eng.
And the title is Notes on Haskell Programming, Part 142.
Right. And the mission of this deep dive is to explore the incredibly complex architecture required to teach a computer how to read human formatting.
We'll be looking at how Eng utilizes parser combinators.
Yes, and the specific challenges of look-ahead assertions and how a developer basically has to program a programmatic U-turn to prevent the whole system from crashing.
Just due to a stray new line character.
Yeah.
Eng's journal is such a perfect case study for this because it deals with a highly specific real-world edge case.
Right. Eng is building a custom text parser and stress testing it against various input file layouts.
Just to ensure it can handle different structural conventions.
And the layout that completely breaks the system involves Chinese web novels.
Yes.
Because these texts have a particular formatting convention that's optimized for vertical scrolling on mobile devices, right?
Exactly. The physical line breaks within the text are sometimes arbitrary. They just wrap based on screen width or sentence flow.
Because of this, structural paragraphs aren't defined by a simple carriage return anymore. They are separated by full blank lines.
Right, so a single logical paragraph might span several physical lines of text before you finally hit that blank line separator.
And the problem Eng documents is that the existing parser was failing fundamentally here.
Yeah, the parser was built with this rigid traditional assumption. It saw a new line character, an N in the character stream, and it immediately concluded that it had reached the end of the current paragraph.
And the beginning of a new one.
Exactly.
But the machine is being perfectly obedient to its programming, right?
Yeah.
It was told that a new line character is a boundary, so it enforces that boundary relentlessly.
It's just following orders.
I was thinking about the cognitive dissonance of this. It's a bit like reading a physical paperback book. You are reading a sentence, your eyes track across the page, and you reach the right margin.
The sentence isn't over, but the page is out of space.
Right, so your eyes drop down to the left margin of the next line to continue. Now imagine if, the second your eyes drop to that next line, a referee blows a whistle and yells, "New chapter."
Oh, wow. Yeah, the reading experience would be completely shattered. You'd have these fragmented, incoherent shards of text being treated as isolated thoughts.
Because your brain knows the sentence is just wrapping around the page. The context is obvious to you.
But the machine, acting as that referee, only sees the physical line break control code.
And strictly applies the rule it was given. Every single line of text becomes an isolated paragraph. The flow is destroyed.
It really illustrates the gap between implicit human context and explicit machine instruction.
Yeah.
We implicitly understand the difference between a new line that simply continues a sentence for formatting reasons and a blank line, two new lines in a row that intentionally separates thoughts.
The parser has zero implicit understanding. So Eng's challenge was taking that human context and encoding it explicitly so the machine could actually execute it.
Right. And since the machine lacks that context, Aang had to rewrite the fundamental rules of how the program defines text boundaries.
And the environment Aang is working in is Haskell, specifically utilizing a library called megaparsec.
Yeah, for those familiar with functional programming, megaparsec is a popular library for building parser combinators.
Which is a really interesting concept.
It is. The philosophy of parser combinators avoids writing monolithic, complex scripts to parse an entire document. Instead, you write microparsers.
Like atomic functions.
Exactly. You write one parser that just recognizes a lowercase letter, another that just recognizes a whitespace character.
And then you combine them.
Hence combinators. You combine them into higher order functions that parse a word and combine those to parse a sentence.
You pipe these small functions together to handle increasingly complex data structures. So Aang has to define a new combinator, a new set of rules for what constitutes a paragraph in the context of these web novels.
Right. In the code, this is called T-paragraph,
Mm.
and Aang redefines it with very specific constraints.
A paragraph is now a sequence of lines that are not separated by a blank line, and crucially, do not start with a header pattern.
The code starts by capturing the initial chunk of text. Aang defines a function called line content.
And the parser advances its read pointer through the character stream, consuming characters one by one.
It uses a command to keep consuming as long as the characters are valid paragraph text, and it stops the moment it hits a new line character.
So it successfully scoops up that first physical line. But because of the web novel formatting, the program cannot safely stop there.
No, it has to determine if the next physical line in the text file is just a continuation of the current paragraph, or if it is the start of a completely different structural element.
Right. Aang's code looks for what they label other lines or remaining lines. But wait, I got genuinely hung up on this part when reading through the journal notes.
Okay, what part?
Well, if we are thinking about the mechanics of the character stream, the parser is moving linearly, right?
Right.
It consumes a character to evaluate it, moving the read pointer forward. How can the parser possibly know what the next line is without actually consuming the characters that make up the separator? I mean, if it accidentally consumes a chapter header just to see what it is, it can't uneat it, right? The structural marker is gone from the stream.
You are identifying the central tension of linear parsing. How do you inspect the upcoming data without consuming it and irrevocably advancing the parser's state?
Because if it eats it, it's gone.
Exactly. If the parser consumes a metadata marker, say a string of dashes denoting a scene change just to evaluate it, those dashes are removed from the input stream.
Right.
When the program eventually calls the parser responsible for handling scene changes, the markers are missing, and the parsing fails.
The whole document structure falls apart just because the paragraph parser ate a token it wasn't supposed to.
It's a huge problem.
Yeah.
But Aang solves this using a look-ahead mechanism within megaparsec called not followed by.
Okay, how does that work?
Before the parser attempts to merge the next line into the current paragraph, it has to check for danger zones. Aang defines these danger zones as paragraph separator.
So a separator could be an end-of-line marker indicating a blank line, or a metadata string like the dashes we mentioned, or a formal chapter header.
Right. The not followed by logic acts as a guard. It allows the program to peek ahead into the character stream to see if any of these separators are lurking just around the corner.
So functionally, it is a negative look-ahead assertion. It is instructed to look at the next sequence of characters without advancing the main read pointer.
It essentially asks, if I were to run the header parser right now, would it succeed?
And if the answer is yes, meaning a header is next, the not followed by assertion fails.
Exactly. Which tells the paragraph parser to stop accumulating lines. The paragraph is complete.
But if the assertion succeeds, meaning there is no header and no blank line ahead, then it is safe to scoop up the next line and append it to the current paragraph block.
Because it verified the path was clear. It evaluates the condition without altering the state of the machine. The tokens remain in the stream for the next parser to handle.
Look-ahead assertions are really powerful, but the notes indicate they only work if the boundaries are perfectly predictable.
Right, that's the catch.
What happens when the text is ambiguous? What happens if the parser has to actually start consuming characters to figure out if a grammatical path is valid, only to realize halfway through that it made a terrible mistake?
That is where the architecture becomes much more complex. Sometimes looking ahead isn't enough because the distinguishing features of the text are buried too deep within the sequence.
So what does it do?
The parser has to tentatively accept a path, commit state, and see if it pans out.
To understand why this is dangerous, we have to look closely at how the parser handles memory and state within the remaining line's logic.
Yeah.
When a parser consumes a token, like an end-of-line character, that token is not just bypassed, it is actively removed from the active input stream.
The machine discards it to save processing power and memory. A consumed character in a linear parser is a rigid commitment to a specific grammatical path.
The read pointer has advanced.
And the previous tokens are basically garbage collected.
So, the parser sees an end-of-line character, an eel. It consumes it, operating under the assumption that it is just a standard line break within a continuing paragraph.
Right.
But then it reads the next few characters and realizes they actually form a chapter header.
The parser recognizes a structural violation. It realizes that the end-of-line character it just consumed was actually the blank line separating the paragraph from the new chapter.
So it needs to yield control to the chapter parser.
But the character is gone.
Yeah. The parser cannot rewind the stream because the previous state no longer exists in memory.
It has violated the document's rules, but it has no valid path forward.
And this doesn't just cause a minor formatting glitch, right? It throws a fatal parse error. The program completely halts.
The state of the parsing engine is irreversibly corrupted. To prevent this, Ang implements a specific function from the megaparsec library.
This is the three-letter function called try.
Yes, try. And its mechanics are absolutely vital for handling ambiguity.
In the journal, Ang uses a highly evocative visual analogy to explain this, calling the try function a programmatic U-turn.
That's a great analogy.
Think about driving a car down a city block. You approach an intersection, you make a decision, and you turn down a one-way street. You commit to the path.
Right.
But halfway down the block, you realize it is a dead end. In the context of our parser, that dead end is the unexpected chapter header.
And without the try function, your car just crashes into the barricade. The system halts.
But when Ang wraps the parsing instructions inside the try block, the behavior changes fundamentally.
Because try instructs the library to cache the current state of the parser before it consumes the next token.
It takes a snapshot of the read pointer's exact location and preserves the current input stream in memory.
It is like saving your game right before opening a suspicious door.
Yes. You drive down the one-way street, you hit the dead end. But instead of crashing, the try function intercepts the failure. It triggers the U-turn.
Your car is instantly teleported back to the intersection,
facing the original direction exactly as you were before you made the turn.
The cache state is restored. The read pointer is moved back to the snapshot position. The consumed end-of-line marker is effectively unconsumed and placed back into the character stream.
You are back at the intersection, and the parser can attempt a completely different route.
It can say, well, that path failed. Let's try treating this sequence as the start of a new section instead.
And if that new path succeeds, the snapshot is discarded and the program continues.
Ang's notes emphasize that this backtracking capability, the try combinator, is often one of the most misunderstood and complex elements of parser combinators.
Because it requires the system to hold multiple potential realities in memory simultaneously.
Exactly. It gives the computer the ability to perform non-destructive hypothesis testing.
The machine needs a safe space to fail. I mean, human language and even structured human formatting is inherently ambiguous.
A new line character can mean a hard return, a paragraph break, or nothing at all, depending on the specific characters that follow it.
So the computer has to be able to say, let me assume this character means X. Oh, the subsequent data proves it was actually Y. I will roll back the timeline, restore the stream, and proceed with hypothesis Y.
It makes the parsing engine resilient to ambiguity.
Yeah.
And from a software engineering perspective, it keeps the individual combinators clean.
Right. The paragraph function doesn't need to be bloated with the complex nested logic required to parse chapter headers or metadata blocks.
It just tries to parse paragraph lines. If it oversteps its bounds and hits a structural marker, the try block catches the error, rolls back the state, and lets the appropriate specialized parser take over.
This journey through Ang's developer journal really highlights a fascinating intersection between human culture and machine architecture. We began with a formatting quirk specific to Chinese web novels.
The reliance on blank lines rather than carriage returns to define structural boundaries.
A convention that completely broke a parser built on rigid, traditional assumptions.
Yeah.
We looked at how functional programming languages like Haskell use combinators to build complex behaviors from atomic pieces.
And we explored the mechanics of look-ahead assertions, how not followed by allows the read pointer to peek down the character stream without destroying the tokens it evaluates.
Resolving the tension of inspecting data without irrevocably consuming it.
But when looking ahead isn't enough, we saw the profound utility of the try function.
The programmatic U-turn. The mechanism that caches parser state allows for non-destructive hypothesis testing and prevents a system-wide crash by rolling back memory when the machine realizes it went down the wrong path.
It is a deeply technical solution to a fundamentally human problem,
Mhm.
which is ambiguity.
Understanding this invisible architecture gives you a totally different perspective on the software you interact with daily. I mean, the seamless experience of reading an ebook, scrolling through a formatted article on your phone, rendering a complex web page, none of that happens by default.
The machine is expending tremendous computational effort to simulate the implicit context that our visual cortex just provides naturally.
Behind the screen, a parser is working furiously. It is reading linear character streams, making look-ahead assertions, caching state, hitting dead ends, and making thousands upon thousands of these tiny hidden U-turns every single second.
It is constantly backtracking and correcting itself.
All so that you can absorb the information without ever noticing the underlying chaos.
Yeah.
The machine manages the complexity so you can experience the simplicity.
It is a true testament to the layers of abstraction we have built into modern computing.
Which leaves us with a final thought to consider regarding the mechanics of reading. We have spent this time analyzing how a computer requires explicit, memory-intensive U-turn programming just to navigate the ambiguity of a blank line.
It has to cache its state and roll back time just to figure out where a paragraph ends.
Think about your own cognitive processing. Think about reading a complex garden path sentence. One of those sentences where you read halfway through and suddenly realize the word you thought was the subject of the sentence is actually a verb modifying something else entirely. Your brain has to instantly halt, rewind to the beginning of the sentence, reassign the grammatical roles of the words, and parse the meaning again. So, how many invisible subconscious U-turns and backtracking corrections does your human brain make every single day without you ever noticing the crash?